So welcome back, and let's see some of the applications of CNN for some of the computer vision applications. And the first one is object detection and localization. So in order to do object detection using a CNN, you would have to run a sliding window along the whole image and then perform classification on these windows. And so first of all, that's time consuming, and also you have problems of scale. For example, if for the hat, you would need a window like this. For the glasses, you would need a window like this. For the person, you would need a window like this. For the horse, you would need a window like this. If that person is very far away, then the window would change the size. So that's a problem using just a normal CNN, a standard CNN to perform object detection. So that's why the region CNN or RCNN has been proposed, and that works with, so you have, so the way it works is you have a segmentation algorithm, a standard segmentation algorithm, which takes this image here, and the result would be a number of blobs. So this is just a normal or standard segmentation algorithm, which is not based on deep learning. And then it would detect, we give you blobs, like a blob here, or maybe a blob around here, maybe a blob here, and so on. And what then you would do is just, so the RCNN, what it does, it just takes these blobs and then perform classifications on them. So one downside of this is that the downside is that it's very slow. You will have to perform classification on a number of so for example, so instead of using just a normal CNN and you would run it on each window, the RCNN is better because maybe you would run it on 2,000 blobs, which is a lot smaller than that. So the downsides of RCNN is that it's quite slow. So that's why the fast RCNN was introduced. And then it uses a convolution implementation of the sliding window to classify all the proposed region. So this is the structure or the architecture of the fast RCNN. And as you can see, and this is the idea to show you the application of CNN for computer vision. It only uses a ConvNet, a fully connected layer, softmax, regressor to perform object detection, which was actually before deep learning, it was quite hard problem. So the downsides of so this is how it works again. So it takes an entire input, and as input an entire image and a set of object proposals, which are obtained using a standard segmentation algorithm. And then the network first processes the whole image with several convolutional and max pooling layers to produce a feature map. And then for each object proposal, you have a region of interest pooling layer, which extract a feature, a fixed length feature vector from the feature map. And then this is fed to two subnetworks, if you want, a softmax that would give you the class of the object. Okay, maybe this is a hat. And then also it gives you the coordinates of the bounding box. So we give you the this bx, by for this point. So the coordinates of these points. Okay. So again, this downside of the fast RCNN, this algorithm is that it uses a standard segmentation algorithm to propose regions, and that's also quite slow. So there is actually, after that, there was another algorithm which is called faster RCNN, which performs the segmentation using a CNN. So it proposes, so these region proposals or blobs are detected using a CNN algorithm. And it runs quite a bit faster than the fast RCNN, but still the performance of the faster RCNN is slower compared to the YOLO. You only see it once. YOLO stands for you only see it once. And YOLO is based on other concepts like the anchor windows and the non-maximum suppression and so on that we are not going to cover in this course. And another network which performs semantic segmentation. So you have the probability for each pixel is assigned a probability that belongs to a certain class, and this is called deep deconvolution network. And this is based on VGG16 network, VGG16, and it has two subcomponents, the convolution network and the deconvolution network. So the convolution network corresponds to feature, so it's a feature extractor. So it will take the input image and then it will extract at the end the number of features, as opposed to the deconvolution layer, which is a shape generator. So it will generate a certain shape and would give you would produce the object segmentation. And actually this shape also is a probability map and just of the same size as the input image, and where each pixel again has a probability that which shows or which tells you whether the object belongs to that to a predefined class or not. So the deconvolution, this deconvolution network is a mirrored version of the convolution network. So instead of having pooling, it has M-pooling. So it has a series of M-pooling and deconvolution and rectification layers, as opposed to the convolution network, which reduces the size of the activations through 4 feet forward. So in this case, the deconvolution enlarges the activation through the combination of M-pooling and the deconvolution operations. So you can see here that it's a mirror version. So you have this is mirrored with this one, this is mirrored with this one, and so on. The last network that we're going to see is a network for action recognition. So you have a series of, so you have a video input or a sequence of frames which showing a person performing a certain action. And your goal is to give a class score, meaning that this is action X, this is action Y, and so on. So you have a certain class. And then it is a two-stream CNN. So the first stream deals with the spatial information. It deals only with the XY or just the frame, the spatial information, while this one, the temporal stream, is based, or it uses as input an optical flow or multi-frame optical flow, meaning that around this frame here, you're going to extract for example, three frames, which correspond to which shows you the optical flow around this area. And then you're going to, for both streams, you can see that you actually have a symmetrical structure where you have conv1, conv1, conv2, conv2, and you see that the dimensions are the same stride, same pooling, And you have also here a dropout. And then at the end, you have a softmax. So this stream ConvNet is going to give you a certain score to tell you that this is class, for example, this corresponds to the class dancing. And this one would, and the temporal stream will give you another score. And you're going to fuse these scores using one of the approaches. There are a number of approaches to determine the final score to tell you whether this is class certain action, okay? So the temporal stream exploits the motion and it significantly improves the performance, while the spatial stream effectively performing action recognition from still images. So it just deals with one frame at a time. I think this is all what we're going to talk about in terms of applications of the CNN. As you can see again, this is using just the normal concepts that we've seen before, but if you want more details or more applications, you can go back to our book, A Guide to Convolutional Neural Network for Computer Vision. And the lectures, these lectures were based on the book and on a number of other references as well, and a number of, and also videos. We stop here and thank you very much.